Okay, so we'll get started for today. In this class, there will be a lot of reading and a lot of homework. And so please work on the homework problem. So chapter 14, we weren't going to talk about it, but I think there's still some important concept in that chapter. So I will have you guys read about it. It's a lot of basic knowledge of periodic table. And please work on these problems, because a lot of these concepts are reviews of last semester. Right now we're on chapter 16, and based on your performance on your concept exam, I think everybody did quite well. I know you guys learned a lot of stuff in high school. So this class is really going to focus on building other kind of skills, such as critical thinking and English writing skill and problem solving skill for chemistry. So we will go through some concepts. Okay, so we'll start with the first activity. So first, do not discuss with your partner. Write down what you think are the most important parameters that will affect reaction rate. So I'll give you guys 2 minutes to think about what do you think are the most important parameter that will affect reaction rate. So what I mean by affect reaction rate is to make it faster or make it slower. What kind of parameters would affect reaction rate? If you already finished, now you can discuss with your partner and to see if you guys all get the same answer. If you have different answer or you're missing some answer, ask your partner why do they think it is an important parameter. Okay, so in high school, you guys already learned about for a reaction to happen, molecule must collide. Everybody remember that? For reaction to happen, the molecule must collide. Okay, collide means they run into each other. So when you think about collision, what kind of physical parameter will affect the aftermath of a collision? What would affect collision? It's about how fast you're moving, right? Okay, so the key of reaction rate will have to do with the number of collision that occurs and how fast these collisions are happening. Okay, so when you have a collision, it doesn't mean reaction will happen. And we'll later discuss when we talk about reaction mechanism. So think about our atmosphere. We have a lot of oxygen and a lot of nitrogen, right? And then they would run into each other because there's so many of them, right? But there's no reaction between oxygen and nitrogen. So this is why we're studying chemistry, okay? We're trying to explain under what condition things will react, under what condition things are, why they're unreactive. Okay, so the most parameter, how many of you get concentration? I think most of you get concentration, right? Or at least your partner did. Okay, so we'll use a bracket. When you see a bracket like this, that means it's concentration, okay? So because the more concentrated it is, it's easier to find one another, right? So it's easier to run into someone when it is during the passing period when you're walking on campus. If you're running around, you might run into some people, right? Okay. Okay, so what other parameter? We know that where does molecule gain kinetic energy from? Temperature, right? The higher temperature, the faster a molecule are moving. So if you remember the physical states of molecule, if we think about solid, liquid, and gas, if you think about the distance between each molecule, obviously in the gas phase, they're more far apart from each other and they move faster, right? Because otherwise you won't be able to obtain something in a gas phase. It will be a solid, right? That makes sense? Then the final things, because I know there's a lot of parameters, we talk about collision, and depending on these two, so these two are the key parameter that affect reaction rate. The collision, I already mentioned the frequency and energy. So we're all on same page, right? So in chemistry, why do we care about reaction rate? I mean, we're chemists, we do reaction, right? So what exactly this rate is? So I mentioned the most important part is concentration, right? So we care about how fast things are reacting. So the easiest way we monitor it is by looking at how fast does the concentration decrease over time, right? So a typical kinetic plot would be having time as your x-axis, and for your y, you can monitor your reagent concentration, or you can monitor your product concentration, okay? But typically, let's start with a curve like this. It really depends on reaction order. We'll get to there in a little bit. So what is rate? So the delta means change over time, okay? So the negative sign means we're losing this compound because it already reacted, it turned into something else. We care about how fast this reagent decrease over time, okay? So you have to remember, when we talk about rate, it could be an average rate, okay, over a long period of time. It could be an instantaneous rate because we already set an assumption that concentration is the most important parameter. So if your concentration decrease, there's less chance it run into another molecule to react, right? So we'll get to the molecularity later. Then we'll have different scenario. So in general chemistry, we make a lot of a summary of a certain phenomenon that we observe, okay? So sometimes it may be confusing. If you're confused, please raise your hand and let me know what are you confused about, okay? So in some cases, you will also see the decrease of reaction rate is like a straight line, okay? It not necessarily to be an exponential decay, okay? And then that is what reaction order is affecting this behavior. Let's look at a simple reaction. Okay, so this is a balanced equation of hydrogen reacting with iodine forming HI, right? So we know when we lose every one molecule of hydrogen and one molecule of iodine, you will generate two molecules of HI. So the formation of HI is twice faster, 2 times faster than the H2 and I2. Everybody agree? Okay? So that's why in terms of displaying the reaction rate of this thing, it's rate equal to concentration, change in concentration of hydrogen over time, and that will equal to the change of concentration, decrease in concentration of iodine, right? Hydrogen, when they run into each other, they're not going to do anything. But when they run into another iodine molecule at a suitable frequency and energy, it will generate HI, okay? So this factor comes from here, okay? So this will lead us to a very simple concept. It's when we balance our equation, our rate expression will look like something like this, okay? You guys will know what this will look like. Just follow this pattern, okay? You do 1 over B, 1 over little b, and changing concentration of changing concentration of A, changing concentration of B, and then for formation, it will be positive because you are getting the product. Okay, that all makes sense? So next thing we'll get to writing more rate law to describe the kinetics of chemical reaction. So a very simple way, or a very simple expression is we know when we do reaction, we mix 2 things or 3 things together, it will generate 1 to 2, maybe 3, maybe 4, and many other products really depend on the condition and the combination of reagents. One most important part in rate law is that we can express the reaction rate as this rate law function. And this m and n are the exponent that explaining the dependence on the reagent concentration. And sometimes people will ask you, okay, what's the order of this reaction? So when they say order of the reaction, that means an overall order, which is the sum of these exponents, okay? So let's go back to the scenario here. When you balance the equation, the number in front of these reagents doesn't necessarily reflect the dependence of the order. It has to do with reaction mechanism, okay? You have to actually do the experiment to get this exponent, okay? There's no way that you can get the dependence on concentration by a simple balanced equation, okay? Everybody get this? You must do experiments. Now I want you guys to take 1 minute to discuss with your partner. How can you monitor a reaction? So think about in high school, how did you guys monitor a reaction? Even on paper, how would you know? How would you do that? Now that you can discuss. And when we talk about reaction, so sometimes if there's color, okay, we can use some spectrometer to look at the increase in absorbance, because color, when we see color, that means there's certain wavelengths, a certain range of wavelengths being absorbed by the molecule, right? So we can look at the absorbance of our reaction vessel, assuming there's no complication coming from your reagent, okay? So we can monitor the absorbance. And second method is a more sophisticated method. I know this is not in the book, okay, because it's in a more advanced chemistry, such as analytical chemistry, you will learn about different analytical technique. So absorbance, this is a new word, spectrometric. That spectra means like a chromatogram is a spectra. If you have, like this would be called a spectra, okay? So it has some informations, it has some numbers, okay? So that is called spectra. So when I talk about the absorbance change, UV spectroscopy or UV spectrometer is a very simple way to look at the color change, right? So there's other ones such as gas chromatography. So if you remember from the earlier chapter, we talk about the London dispersion force. Every kind of molecule, they have some sort of interaction with each other. The matter is how strong these interactions are. So based on their strengths of interaction with your column, so you can pass your, let's say you have a tube, right? And there are certain material present in this tube. Depending on how strongly your reagent or product interact with these tube, it's going to take them different amount of time to pass through this tube, okay? So you can enable separation. You initially have a reaction mixture, you can separate them. If you have some standard, then you will know exactly what these things could be, okay? Then you can get reaction rate, okay? So you monitor your reaction with some more advanced analytical technique, okay? So in the case where you can form solid, you can, so let's say you do a reaction, it's a gas-phase reaction, okay? Then you are forming some solid, you can measure the weight of your product, right? And then you can look at different time, how does that mass increase over time. For the aqueous system, when you do reaction in water, you can measure conductivity, right? There are certain reactions that will change the ion concentration. Again, go back to a parameter that affecting the reaction rate is that you can monitor concentration of ions based on conductivity of your solution. And the third method will be monitor the pressure change of your reaction. For example, in this case, there's going to be a pressure change over time, right? But of course, we have to go back to the nature of a reaction and how your reaction is set up. And we'll discuss more of it in thermochemistry session, okay? So in thermodynamics, it deals with expansion and of your volume when we have a combustion, right? So we know what combustion is, right? You burn something as a combustion reaction. You turn a liquid or a gas into some other oxidized product. After you do the experiment, you can fit the data. I want to point your, so in your book, when you go back today, I will have you guys read page 702 and 702, 704. I think it's very simple. You guys may already done that before, okay? To figure out reaction order based on the experimental data. And then to make your life easier, a lot of these problems in the book or on my test, we will use very simple numbers, okay? So you just have to look at when my concentration double, does the reaction double? Does the reaction rate triple? That will tell you what's the dependence of your concentration for the reaction rate. Okay, that makes sense? So a lot of times we'll do a very simple method. We keep one parameter the same, changing the other concentration, okay, the other parameter, and monitor the reaction rate. Okay, so we will do some plot like this and extract information, reaction rate from this plot. Okay, so how do we extract reaction rate? We do this, okay? So that should be simple enough. And you can do some simple math and solve for this n or m. And then you can get the overall reaction order by adding them together. Let's go to sample 16.4. So it's on page 706. For those who already taken the concept exam, you guys seen some problem like this, right? Okay, so this is because there's different way people learn. When I was in the US, people find that visualization, or at least a mental visualization, is a very important way to gain understanding on how fast your reaction progress, okay? In this book, you will see a lot of problems look like this, okay? But I've also seen a similar problem in some experimental high school textbook. So I think we should get familiar with this if you're not familiar with the diagram here. Here it's basically, we will have to observe the change in this picture. So again, we go back to the first parameter, okay? What's the first parameter? Concentration, right? Okay, remember that reaction rate dependent on concentration, okay? So we can simply count the number of these red balls and blue balls, right? Then see the change in different experiment number 1 through 4, okay? So if we look at the number 1 and number 2, the number of blue balls are the same, and the number of red balls double. And what happened to the reaction rate? You can see the number, right? The reaction rate doubled. What does this tell you? When my concentration doubled, my reaction rate doubled. What the exponent should be? It should be 1, right? So this is what I mean by looking at the experimental data and figuring out the reaction order. Okay, and remember that it doesn't have to be 1 or 2, okay? It could be 1/2. It's in some cases. It has to do with reaction mechanism. Okay, so then you can compare experiment 1 and 1 to 2 to 3. Then if you look at experiment 1 and 3, the number of red balls are the same, right? And what happened to the blue balls? Blue balls double, okay? And then look at our reaction rate. It increased by 4 times, and that's why our reaction order is 2. Okay, so what's the overall reaction order of this reaction? Discuss with your partner. Okay, that should be simple, right? We simply add those 2 numbers together. So in that particular example, we can write, let B be blue ball, okay? So the blue ball, the dependence is, and we'll call this red, and this would be 1. Overall reaction order will be 3. So when you go back, so instead of assigning the whole chapter this semester, I'll try to assign specific page. Okay, I know you guys are all busy, but please make sure you actually read the book. Okay, for when I learned general chemistry, I basically, I would go to lectures, but I spend a lot of time reading this book. There's a lot of examples, okay? And if you are ambitious, you can look at the follow-up problems. That helps you to gain better understanding. All right, so we'll briefly touch on the integrated rate law. So if you remember the concept exam, okay, so I don't really need you to derive a lot of math, okay? This is a chemistry class. We focus on understanding of concept, not math. But you should be able to work with the data, okay? In the future, you guys will have a lot of data from your experimental courses. Then you have to learn how to process this data. In the next period, we'll talk more about integrated rate law. So let's go back to this plot, okay? We monitor the change in reagent concentration over time, right? So I mentioned, most reaction will look like this, okay? But in some cases, it may look like this, okay? So this basically show you that, okay, it's decreasing, but the rate is constant throughout the reaction, independent of your concentration, right? So this will be a typical plot for a zero order reaction. When you see something like this, I mean, this is a very poor drawing, right? And then you can obviously go to Excel, typing an equation. You can type in equation like this and just put in some random number, 1 or 2, okay? And then you can set your rate constant to be 1, okay? And then you can plot a data to see when you change the number, after you do the math, what kind of number output you will get. So the first order and second order reaction, it will all look like this. Unless you do further processing of the data and fit your data, you can get an idea of what your reaction order really is, okay? So class is over.